Related rates are when a formula relates rates. Well, what are rates? Rates are rates of change. Rates of change are slope. So they're derivatives when they're related by a formula. Okay, and these are real-world applications, so things are changing with respect to time. So when we take the derivatives, we're going to be using a ddt. So let's say I have this conical tank and it's filled with water and the water's draining out of the tank. So my water level is changing. It's getting lower with time. Okay? And the way I'm going to relate all the variables here is that this is the volume of water, and the formulas, you can either look them up. Most calculus textbooks have them either on the inside of the front cover or the inside of the back cover, all the geometric formulas that you might need for these problems. But the formula for the volume of a cone is pi over 3 r squared h. So as time goes on, the height, the radius, and the volume of the water are all changing. So here, my radius at the top of the tank is bigger than it is now that a bunch of water's drained out of the tank. The height is shorter now than it was when it was filled to the top of the tank, and the volume is now less. So if we take the derivative of both sides of this equation, that'll give us how everything is changing with respect to time. So if I do the derivative with respect to time of v and the derivative with respect to time of the right-hand side, well, I'm just going to get dv dt on the right-hand side, or on the left-hand side. On the right-hand side, this is going to be a product rule because r is changing with respect to time, and so is h. And pi over 3 is just a constant that's going to stay out front. So my derivative is derivative of the first, well, that's pi over 3 times 2r, and r is a function of t, so we put a dr dt there, times the second, so all of this was the derivative of my first function, times the second function is h, plus my first function times the derivative of the second one. H is a function of t, so its derivative is dh dt. And I can clean that up a little bit and rewrite it as pi over 3 times 2r dr dt h plus r squared dh dt, just because it's a little bit easier to look at. And so that's the type of situation we're going to be working with now, and then we're going to be given information about some of these quantities, and we're going to find information about some of these quantities. So let's start with a really easy one, okay? This one, I'm not even giving you a geometrical situation. I'm just straight up giving you the information that you're going to need to solve this problem. For every problem, in order to organize our information, we need 4 things. We need to know, what are we given? What are we being asked to find? When are we finding it? And what is the equation that relates all my variables? So here we have x and y are functions of t. They're related by y equals x squared plus 3. So that's my equation. I can go ahead and write that here. That's y equals x squared plus 3. I'm being asked to find dy dt when x equals 1, given that dx dt equals 2 at that x value of 1. Okay, so once I have all my information organized, then I want to take the derivative of the equation. So we're going to ddt both sides of our equation. And the derivative of y is a function of t, we're just going to get dy dt. And when I take the derivative of x squared, I'm going to get 2x times dx dt because it's a function of t. And the derivative of 3 is 0. So I have everything I need now to solve for dy dt because I know what x is. X is 1 from over here. I know what dx dt is because it was given to me here. So we just need to plug in, and I get dy dt equals 2 times 1 times 2 equals 4. Okay, so that example demonstrates the process we're going to use. But now we're going to start getting into the word problems that are actual geometric applications. Okay, so I think everybody's probably seen this in real life. A pebble is dropped in a pond and it causes ripples in the form of concentric circles. You know how if you throw a rock in the middle of a pond, you'll see the ripples and they spread out until they reach the edge of the pond. The radius r of the outer ripple is changing at a constant rate of 1 foot per second. So what piece of information was I just given?
The rate of 1 foot per second.
Which is dr dt, right? So I was given dr dt equals 1 foot per second. When the radius is 4 feet, so there's another piece of information. When r equals 4 feet, what is the rate of change of the total area of the disturbed water? So I'm looking for the rate of change of area. That's a derivative, so we're trying to find dA dt. So what's left is the equation. So we're dealing with a circle. What's the equation for the area of a circle?
Pi r squared.
Yes, area equals pi r squared. Okay, so we want to take the derivative of both sides of our equation, so I'm going to take the derivative with respect to time. And on the left, I'll get dA dt. And on the right, pi is just a constant that stays out front. Derivative of r squared would be 2r times dr dt. So, this is what we're trying to find. And if we go back and look, our r is 4 feet and our dr/dt is 1 foot per second. So, the rate of change of the area of my outer ripple is 8 pi feet squared per second. And feet squared, those are the units for area, right? And because it's a rate, it's per second. It's how it's changing over time. So that's how area is changing over time. And that's our answer.